Interest include synthesis, RF transceivers, and millimeter wave circuit design. I welcome both the speakers to the session and hand over to Dr. Prince to start the session. And he will be delivering the session on the current trends in semiconductor SoC design. Thank you.
Thank you, sir. Am I audible?
Yes.
Thank you, sir, for the invitation. And it's a great honor to present this topic here. So let us
make it full screen.
Yeah. Hello, Mr. Can you see this?
Yes, you can go.
Yeah. So today my topic of presentation is recent trends in semiconductor design. So here we will be briefly reviewing the different sectors and the technological advances that propel the semiconductor growth. So yeah, semiconductor, you see, as you are all aware, we are using several semiconductor devices in our day-to-day life, starting from the mobile phones, laptops, and it impacts in our every day-to-day life. So if you see this graph, the semiconductor market has risen exponentially in last several from the last decade, and it is anticipated that at 2030, this semiconductor business will achieve 1 trillion business market. So this is a projection. So currently we were almost at 500 million market. So it will reach 1 trillion by 2030. And what are the sectors that propel this semiconductor growth? So the 40% of the growth is due to the high performance computing, that is AI, machine learning and AI hardware, and 30% is due to mobile, and 15% is due to automotives, and 10% remaining 10% is due to IoT, and remaining 5% is due to other designs. And see, we are in the last less than 2 years, the generative AI significantly accelerated the computing needs. If you see last less than 2 years, the ChatGPT and other AI tools came into picture. Because of that, there is, if you see the last 2 years computing requirement, it has risen 10,000 times. So that means when the computing requirement rises 10,000 times, means there is a huge requirement of hardware, especially GPUs and memory requirements. So this has sharply propelled the demand or need for the semiconductor business. So it will not stop here. It will go exponentially high. We don't know where it will reach, but it is keep on rising the demand for the semiconductor industry due to this generative AI and other computing needs. And if I see the companies that are working in the semiconductors, the first one is integrated device manufacturers. So this type of companies, they will design the ICs, then they will fabricate it, and they will sell the chip. Whereas the foundries, they will not design the chip, but they will fabricate it. There are another type of companies that is fabless. So those companies, they will design the chip circuits, but they will send to the foundry for fabrication, and later they will sell it. So these are the three different types of semiconductor industries currently running in the market. So for IDM, see, you can see Intel, TI, Global Foundries, Samsung, etc. They will design the circuits. They will fabricate they have their own fab. They will fabricate it, and they themselves will sell it. But there are some companies that is they will accept the design from other companies. They will fabricate it. So those are called for example, that is TSMC. Fabulous companies are many. So here, we can see Qualcomm, Nvidia, AMD. These are all fabulous companies. They will do the design. They will send it for the foundry, and later they will sell it. So these are the overview of semiconductor companies. So if you see this graph in 1987, 75% of the markets are driven by IDM companies. But when it comes to, and the fabulous companies are just 2%. But when it comes to 2030, we can see that the number of, the percentage of fabulous companies are increased to 23%. And whereas the percentage contributed by semiconductor contributed by the IDM companies is 50 percentage. It's reduced to 50%, 55% to the total market share. But it is projected that in 2030, 50% of the semiconductor market is shared between fabless and system companies. That is a projection, and IDM market share by the IDM companies is reduced to 30%. Because most of the companies are going for fabless because running the fabrication plant is very expensive. So they can concentrate on one design, and they can introduce new products into the market much quickly. That's the one reason. So if you see this advanced technology node, oh, sorry. If you see this advanced technology node, semiconductor process technology has undergone a significant evolution over the past decades. So this will continue into the future. Lithography progress from single pattern immersion to patterning double patterning with the self-aligned features into the print increasing to print increasing smaller critical dimensions. Now lithography has well centered into this EUV era, where the pitch scaling still continues. Now, if you see this, we are now at the 3 nanometer technology node. And the device architectures migrated from the planar to FinFET at the 16 nanometer node. Today, the industry continues the scaling of transistor dimensions by transitioning to nanosheet devices. This progression in lithography and device architectures, new materials, integration schemes, and novel features will continue to drive the scaling of future products in power, performance, and area for each technology generations. So looking into the transistor architecture outlook, vertically stacking NFET and PFET to create what is known as CFET. See, earlier now it's FinFET. From FinFET, it is moved to nanosheet device architectures. Now, again from nanosheet to CFET. So, so this CFET could provide significantly density scaling benefits. Beyond CFET, low dimensional channel materials could enhance further dimensional and energy efficient scaling. So beyond CFET, beyond silicon, if you see till CFET, we can do the scaling. Beyond CFET silicon, we have carbon nanotubes that is currently in research. So if you see the technology advancements enables energy efficient compute, this using this graph shows the technology advancement enables energy efficient compute. So using power efficiency as the metric and 28 nanometer planar technology as a reference, FinFET technology from 16 nanometer to latest 3 nanometer provided a 10% improvement as shown in left chart. Okay, the performance is 10 times increased. If the density benefits are included, then 28 nanometer to 8 nanometer brings over 80%, 80 times improvement in power, in performance, power, and area. That is shown in right side graph. So this actually shows how that the technology when the technology nodes are reducing, how the performance affects. So it's a great performance improvements when that technology node is getting advanced. And currently, so in the various advanced packaging and chip level integration solutions have been developed over the years, including chip on wafer on substrate, integrated fan-out package, and system on integrated chips. These integration schemes can integrate over 500 billion transistors on a packaged system. Okay, so this is a more advanced packaging system has emerged that creates a more transistor density on a packaged IC. So, okay, let's see what are the applications that fuel this semiconductor growth. Okay, we'll see step by step. So therefore, we'll see overall, you can see that applications lies in automotives, data centers, consumer electronics, telecom, networking, and in industrial electronics. But we'll see briefly what are the those applications. See, this graph shows that around in 2025, almost per day, per year, in 2025, there are almost 2000 billion photos are captured per year. That means billions of image sensors are sold worldwide. So because of this, there is a huge market for the image sensors. And not only the image sensor, we need to store these images to somewhere. So there is a great need of storage devices as well. And if you see this image sensor, you know that image sensor is the eye of a camera. So what does this? It will capture the image. So it will convert to some voltage or current. Then finally, it will convert to digital circuit, and finally the different processing will be taking place and at the digital level, and we'll get a a nice image. So there are lots of advanced uh, uh, advanced evolutions have took place. So if you see here, earlier front side illumination was the main principle behind the camera operations. That's many years back. So that means when you see in the camera, we have photodiodes. The photodiode's main function is to convert the photon of light into an electrical current. So there are different pixel circuitry, the different pixel circuitry. Each there are 3T, 4T, different type of pixels. So these pixels, so when the light enters into the image sensor, first the light in the front side illuminated cameras, the light travels to the its corresponding its the analog and digital circuits, and finally it enters into the photodiode. So the photon of lights are getting shared between different circuits, and only few number of photon lights are entered into, not few, but there is a moderate amount of photon of lights are entering into the photodiodes. So there is a degradation in the image quality. Whereas the backside illuminated, it's came after the front side illuminated image sensor. So the people solved this issue by going for backside illuminated image sensors. So backside illuminated cameras, it will just flip, it will just rotate. So that means whatever came down, it will come on top. So the image sensor photodiodes are on the top. So the light directly falls on the photodiodes. Then we'll get nice image. We can capture the image. We can capture the light, and we can generate the pixel can generate the corresponding circuitry, the corresponding uh, current proportional to the incoming light. But even there are some disadvantages. The main disadvantage is that, see, this image sensor, these are all placed on one wafer. So the fill factor is of the image sensor is little reduced. And to solve this problem, we are going for stacked backside illuminated image sensors. So in this, what it does is the circuit and the photodiodes are placed apart. That means one wafer is the top wafer is full of uh, the photodiodes and the different filters, color filters, and the bottom side, the top side is for these are photodiodes, and the bottom layer is its corresponding circuitry. It is a mixed circuitry, and both analog and digital. Again, here also there is disadvantages. The main disadvantage is several disadvantages there. That is mixing of analog and digital circuits. So the switching noise of the digital circuit can impact the analog circuits. Again, because analog circuits are of high volume. Sorry, this bottom second layer circuits that consists of both analog and digital have high volume. And again, you need to add dummy layers on the top of the photodiode, on the top close to the photodiode. Again, that will affect fill factor. So people, for the latest cameras, it is a three wafer stacked backside. Three wafers are stacked. The top wafer is for the photodiodes, and this second and from the two stacked backside illuminated, we have second two wafers. We have the wafers. We have the wafers. Those wafers are divided into two different wafers. That means you can say that second wafer is for analog circuits, and the third wafer is for digital circuits. We can just imagine like that, but it need not be. Okay, this is the current current advancement in the a CMOS image sensor. So because of this, you can say that fill factor is greatly improved. Fill factor is the ratio between the photodiodes and the remaining analogs, remaining circuitries in the camera. So now if you see, the top layer is full of photodiodes. That means it will capture whatever light incidence of incident on this. So the image will have very good quality. Okay, this is the latest innovation in the CMOS image sensors. This is what it shows: single layer photons and single layer pixel. Can see that T1, T2, T3, T4 are transistors, and later this T1 for 2 layers. These are on the top layer and bottom layer, and most of the T1, T2 are transistor circuits, and those are on the top wafer, and T1 is only placed on the top bottom wafer. So here is clear. I can see that how the two wafers are stacked and how 3 wafers are stacked. If you see the 2 wafers, the photodiodes are shown in pixel, shown in written as pixel, shown in green blue color, and when it left and right side, dummy areas are filled. That is just to cover the readout and processing and storage circuits beneath this top layer. The top layer is um, our pixel photodiode layer. But so you can see that in this 2 wafers stacked, the extra dummy areas are filled. So there again, some lights will fall on these dummy areas, and we will lose the fill factor. So in 3 wafers stacked, you can see that the readout and processing are placed on one separate wafer, and storage is placed on another wafer, and the photodiodes are completely on separate wafer. So when the light falls on this type of cameras, this photodiodes completely absorbs this light, and it will process and generates a very high quality image. Next, we'll see what is the next advancements in semiconductor design. If you see that in last decade, there is a huge growth in neuromorphic electronics. Anyway, it came much before, but in last few years, we have seen that there is a huge requirement in neuromorphic electronics. What is actually neuromorphic? Neuromorphic, in simple words, we can say that it's a hardware that mimics the biological neural systems. So we have different neurons in the brain. So those we can model in using hardware. So whatever the biological neuron systems, when we model using some analog or digital hardware, then we can say that that is a neuromorphic electronic device or system. So just to explain it, it's briefly. See here, the first image, how our human brain recognize whether the input image is a dog or cat. So we will just to make you understand, we are going very briefly. So just see when an image falls on eye, that is the retina of the eye. So this retina converts the incoming image into spike trains. So that is spikes, or more, you can say that it's a kind of continuous time signal, but it is proportional to input image. But okay, so the spike rate is proportional, or the spikes are proportional to the intensity of the input image, and this spike is output of the eye, and these spikes will have all the informations about the input image, and this will enter into our brain, and brain will process it, and our brain will process it, and it will identify that uh, whether the input image is a cat or a dog. So how we need to model this, and we need to convert this into a hardware, so that you can see, if you see in place of eye, we'll have a neuromorphic sensor. In place of human brain, we'll have a neuromorphic system that will process these spikes. Actually we are trying to implement our biological intelligence on a chip. So this hardware, if you see the bottom hardware, this will exactly, it will work as a human system. So there are different types of neuromorphic sensory and processing systems. So first one, see, these are silicon. If you say there are sensory systems. So the first one is you can silicon retina, then silicon cochlea, and xenomorphic nose. So the silicon retina is a vision sensor. It is sensing uh, the, that is inspired by the biological eye, whereas the silicon cochlea, it is hardware that mimics the hearing and auditory signal processing that is taking place in our cochlea of our ear. And neuromorphic nose. So this is it's a bio olfactory sensing. So actually, it's a hardware that try to detect the smell of some gas. Sometimes see its application comes in see certain areas there are poisonous gases. So we cannot uh, we need to get a smell of that. So in that we can use this neuromorphic nose, because if human if we, humans for humans this basis of will be much dangerous, because there will be some poisonous gases. So in those cases, we can use a neuromorphic nose. And there is neuromorphic brain chips. So this does the neural processing and computation that is taking place in our brain on a silicon. So, but all these are huge demand. So we will see what exactly all these are. We will see briefly. So silicon retina, uh, actually it came much long back, and its developments are going on. So another name of silicon retina is a neuromorphic vision sensor, or DVS camera, which is it is developed by ETH Zurich. So as compared to normal cameras, silicon retinas it has huge several advantages. See, normal cameras, the images are captured uh, frame by frame, right? So whenever it does not differentiate whether the image is a static or a dynamic, it will just capture it. Sometimes we do not need a static image. Most of the time, we do not need a static image. For example, you are placing a camera on your house. We don't you say in front of the house there will be car, or some stationary objects will be there. We don't want any information from that object. But even using this normal cameras, we are burning too much of power. It is continuously, it is this static images are being captured. But we want whenever there is a motion taking place, we want to capture that image. For example, let's say some animals came to the home. There's a motion change, or some thieves come into the home. So there's a motion. There's a change in motion. some dynamic image. Whenever it comes, we want only that information. In such cases, silicon, this retina or DVS cameras can be used. This neuromorphic vision sensors can be used. So whenever there is this DVS cameras operates whenever there is a change in scene. Normal cameras, it is always on. But this neuromorphic vision sensor or neuromorphic or silicon retina, it will be on whenever there is a change in scene. Means whenever there is some movements on the uh, scene, that movements only will capture. That movements only will be captured, uh, and it will be sent. Another advantage of on this is that, see, no, its dynamic range is too high. It can capture any kind of images, and this device cameras, this kind of sensors, it has inbuilt processing is done within the pixel level itself, so the circuitry is very compact. But if you see a normal camera, this common normal cameras have several circuits. So they are, along with the photodiodes, it has 3T 40 pixels, then CDS circuits, then photo source followers, CDS circuits, ADCs, then digital processing circuits. There are different kind of circuits. So the area and power consumption of a normal camera is too high. Whereas this complete processing that is taking place within a normal camera will be taking place in DVS camera in normal within few transistors. That is because we are trying to mimic the eye. So another thing what I want to point out is that, see, when you are looking at an object, you, our eyes are more prone to moving objects. Our eyes are not it's not more prone to a stationary image. So that is the technology, the idea behind this kind of vision sensors. So again, there is another dynamic audio sensors that is built, or we can call it a silicon cochlear, that is also built in ETH Zurich. And there are neuromorphic processors. So you can say that there is Intel Lohi. This is a neuromorphic processor. This processor mimics the brain. They are trying to mimic the brain of human brain on a hardware. So
I think we have lost
yeah, you can hear me, no?
Dr. Prince.
Hello, you can hear me? Hello,
Yes. In
you can hear,
between,
no?
we lost. Yes. Uh,
Yeah,
Hello.
yeah, I can hear.
Yeah, we can hear you.
Yeah, okay, yeah. Uh, Okay, so we are speaking about Intel Lohi. So Intel Lohi is asynchronous multi-core chip for simulating spiking neural networks, and it has on-chip training, that is plus point, and it consumes very low power, and it is optimized for portability and scalability. And Spinnaker, it is implemented by a group, Corbus group at University of Manchester. So it is a ARM-based simulated spiking neural network. It has a custom digital computing architectures, and it is fully programmable. It is optimized for spiking computational neuroscience simulations. In another neuromorphic processor, it is implemented by IBM. True North is called True North, and it is a asynchronous multi-core large-scale uh, spiking neural network. It is reconfigurable, It is optimized for low power, low latency processing task. So along with this DVS and these neuromorphic processors, we can find out several applications. We can use along with this neuromorphic sensor, plus a camera, along with this processor. We can use in advanced autonomous driving systems. Let's so when let's say whenever some object comes while driving, we can use this sensor DVS camera to capture that image, and the neuromorphic processor will process that image, and it will identify what it is. Based on that, the brake can be automatically pressed, or the speed of the car can be reduced automatically. And there are several applications we can find out. Not only in defense sectors, autonomous vehicles, drones. So many, if you explore, we can find out several applications along with along with silicon radar or neuromorphic camera and and neuromorphic processors. If we combine both this, we can find out different practical applications, and it's being used. And there's another processors that is developed by IMEC that is also similar to this processors. Okay, then next is AI accelerators. These also have this also accelerated the demand of the semiconductor design. So there are different AI accelerators. So it's actually AI accelerators are specialized hardware designed to speed up AI or ML workloads. So we all of us know this, I think. So GPUs, TPU. So GPUs are very flexible. It's very high. Offers very high performance, and it offers training and inference. TPUs, tensor processing unit. It is also a very high performance accelerator optimized for tensor outputs. It operates on large scale workloads. Neural processing units. This also is uses in mobile inference. It's low power, and it is in on-device AI. And another popular accelerators are implemented using FPGAs. It is more customizable, and it offers low latency, and is prototype and easy to deploy. Another is application-specific integrated circuit type of AI accelerators, and it is very efficient, and it is power consumption is also very less in this. It's mainly used for some specific applications. So actually, these accelerators are divided into two groups. So one is the accelerators that are used for the data centers. So GPUs, TPUs are for data centers. So whatever that's on cloud. So whatever we do on ChatGPT and all. So it will process on data centers. You'll get it back. Another kind of AI accelerators are used at the edge. So NPUs, FPGA, ASIC kind of AI architectures are used at the edge on some particular devices. Another systems that does propel the growth for semiconductor is memory. See, memory is a very massive volume market. All kind of PCs, phones, server, and everywhere you need memory. Without memory, it is impossible to run any semiconductor sector. See, if we have cameras, we are capturing the image. We need to store that image to somewhere. So we need memories. So memory in most of the semiconductor companies are investing huge amount on memories. So memory market is it is a huge semiconductor market. So there are different kind of memories, say, dynamic random, double data rate DRAMs. So these are generally called as we say call it as RAMs. So it is used in laptops. So the advantage is that we can um, if we want to enhance RAM, we can enhance it in the laptops and all. So in this kind of DRAMs, the speed is actually now presently it is at DDR5. So DDR5 offers a speed of 12 to 14 Gbps per pin. There are different pins. The signals are passing from let's say we have in the computer we have a controller, memory controller, and we have a RAM. So the information from the CPU or data from the CPU should be stored on the DRAM. So this transfer will taking place through different pins. So each pins have a speed. So DRAM has a speed of DRAM latest DDR has a speed of 12 to 14 Gbps, and this DDR is mainly used in servers and consumer PCs, and the LPDR is a low power DDR. It's also same as DDR, but it is largely used in mobile phones. Its architecture is very same, but there are some circuitry that is designed to consume very low power. And architecture wise also there are difference, but rest everything is same. But the advantage is that it consumes very high, very low power, but the speed rate of the DDR and LPDR are always same. And this is kind of LPD memory is used in edge inference automotives, especially in cars and all. We use LPDDRs because it consumes very low power. We are at LPDDR5. Everything is same, but the power matters here. Another is graphical DDR. So in graphical DDR, the per pin speed is 16 Gbps, gigabits per second. 1 second, 16 gigabits per second will be transmitted from one side to another side, from memory to controller, or from or vice versa. So these are mainly used in graphics, AI inference, and also it is used in automotives. There is another kind of memories that is called high bandwidth memory. So these memories it has very high bandwidth. This memory is actually on one single package. There are many DDRs are placed. Okay, so this is a one single package. HBM is designed on a single package. So in that package, there are different DDRs are placed. Each DDR can be of a speed of, each pin of the DDR can be a speed of 6 gigabits per second. And these DDRs are, or the die of each DDR is placed close to by, and these dies are connected each other. That is die to die interconnections will be there. And there's an interposer that will that's kind of substrate that we uses for this kind of connections. And actually the idea is that it is a single piece of packaged IC. Upon that there are different DDRs are placed. So let's say if one DDR pin, it has a pin of 64. If you placed this kind of different DDRs on a single packet IA, the pin size will be increased to 2000. That means the bandwidth offered by HBM is very high. So we say, so this kind of high bandwidth memories are in current research, and it is designed in industries. So it offers very high bandwidth memory, and it is used in high performance computing, that is AI related applications. These HBMs are largely used, especially in data centers. And it is each DDRs are placed between close by, means DDR, it's die-to-die interconnections. So now we are at the start of the golden age of semiconductor innovations. From the economics point of view, semiconductor technology has a multiplier effect on various sectors. So it is expected that the total foundry revenue will reach around $250 billion by 2030, and it is driving it is driving and approaching 1 trillion semiconductor market. And because of this growth, there is a 3 trillion electronic market, and there will be a 12 trillion IT market. This market business is taking place, is expected to take place by in 2030. And this and if you see this, we can say that so our semiconductor innovations have a multiplier effect. So when semiconductor when there is a growth in semiconductor, it impacts the other sectors as well, because all other sectors, everything depends upon the semiconductor chips. So semiconductor design is a very promising design. So here I just briefly touched on different sectors that fuel the growth of the semiconductors, starting from the devices, packaging, and different applications I have touched. So remaining will be taken by the second speaker. Hello.
Yeah.
Yeah.
Should I start?
Yeah, yes, yes, go
Yeah.
on.
Yeah.
Yeah, I'll try. Start.
So I think after the second talk, we can have a question and answers.
So how much time I have now? Can I have some estimation how much time I have?
You 40 minutes.
So is my screen visible to all of you?
Dr. Prince, can you stop sharing?
Yeah. 1 minute.
Please let me know if my screen is visible so that I can start. Prince, I think your screen is still visible,
It's
right?
not visible. Not visible.
Your screen is visible, I think.
Right, let's see. I stopped. No, I stopped sharing it.
Okay. Is my screen visible now?
No, I think no, it's not visible.
Is it not visible?
I will
start practice.
I will leave and you can enter it again. I will rejoin it.
Yeah, I think now I can. So is my screen visible now?
Yes.
Yes, thanks. Yeah. So I'll just. Okay, so it was very interesting presentation by Prince, and even I got to know a lot of stuff, how the things are going, and I'm more in RF and analog, so I may talk more on that. But still, I'll try how the topic goes. Let's see. I'll start with some recent trends in semiconductor, which Prince already taken, and we'll see some application that is going to change future or some more application going to join us. And we know that AI is also coming in semiconductors, so how AI is impacting and what will be the future applications. And I'll also introduce some circuits so that we can have some more interaction. So I love to have some bidirectional communication. If I'll go in one direction, then it sounds so interaction will be always good. Always good. Please stop me anywhere and have some any random questions. I'll be love to answer it. Or if even I'll learn it because I don't know. Nobody knows everything, but I have potential to error. I have potential to error, right? So please help me if I go wrong somewhere or if you have any questions. So I cannot stop myself saying that we are all moving towards Moore law, but Moore law means every year the semiconductor number of transistors in the chip will increase twice, right? So this is what the Moore law says, and we are so it's going slow now. We are not exactly doubling every year now; it's getting slow, but it's happening. The devices size are shrinking more. So now I think if you know the mobile phones and also we have 5 nanometer, 2 nanometer device size, right? So these all we when we talk device size, we all talk about digital domain like microprocessor, memories. So all those comes under digital and the shrinking helps there. So, but in analog, so what is analog? Analog is like your all the sensors, analog to digital converters, front ends, power amplifiers, all the edge devices. I think edge devices means all the sensors transducers that we use, like cameras, speakers, mics, Wi-Fi, Bluetooth, all the end thing, right? This all are analog. So analog has it has circuits in millimeter, it has circuits in RF. So that's what our analog says. We cannot shrink more, right? So analog talks not on Moore law, it talks more than Moore. So this is what new word now coming up, more than Moore. So analog devices are moving more than Moore. Means we don't want to shrink more because analog devices need something else. Let's try to see what all things analog needs and what digital design don't need. Whereas we see in analog, we are more concerned about gain, linearity, and the noise, right? And the headroom and the matching and all. So these things are not constrained in the digital domain, where the data is just 0 and 1. We don't care about what is in between 0 and 1. Whereas analog, signal is a continuous from 0 to entire voltage source, right? So we have we are as an analog guy, we are concerned about linearity of the signal, how much noise is contributed, and headroom. So we don't want to shrink our device. The more we shrink, we lose our gain, linearity, and noise. That's one of the strange thing that happens when we shrink. So we don't go towards more. We are going more than more. We don't want to shrink more. We want to stop ourselves somewhere in 22 nanometer, 45 nanometer, 60 nanometer, 65 nanometer. So people have stopped. The analog designers have stopped at, I think, even 22 nanometer or 12 nanometer. I don't know exactly. So those things are there. We are not shrinking much. And what happens when we shrink more? Obviously, the parasitics of the device increases and flicker noise. So if you know about parasitic, I'm actually using. So if we know about MOS, we all know that the gap between these, right? This in the MOSFET, we have an extra capacitor, which we call CGD, right? We have extra capacitor which comes here, parasitic part. So even though this is shrinking, this L, the channel length is shrinking, the parasitic is really tough. So as we shrink more, parasitic effects are getting, it's very tough to match, tough to reduce it. Whereas flicker noise is completely proportional to the area of the device, right? So we're trying to reduce the area, where flicker noise is going to increase. So analog devices, analog designers actually get frustrated and get hard time to design if it's a very small devices, right? So that's why instead of going to 5 nanometer or 7 nanometer, the analog designers stopped themselves at 28 nanometer, 48 nanometer devices, and they are sticking themselves to different technologies like CMOS, CG, GaN, so all those things where the technologies are mature and stable, so that we can just do our analog designs. So we'll talk more on analog designs. So what is more than more? So more than more says that uh, we cannot get more help. So we need to just improve with respect to our power management circuits. Where power management circuits comes, we have DC to DC converters, LDOs, and battery chargers. These comes under power management ICs, where these ICs are everywhere. The camera, it has camera, RAM, processor, everywhere you need power management ICs, right? So innovations happens here. So shrinking is not possible. And ADCs, these are one of the important stuff in our computers, right? Our signals, all the signals are converted to digital or digital to analog. When we suppose I'm talking to you, so what is happening at my end? My analog data is converted to digital, got modulated, transmitted, and then again digital data got converted to analog and went through the speaker, and you are hearing it now. So without ADC, I don't think we'll be able to talk, right? So so that part is always there. We have analog to digital converters, and high performance analog to digital converters are needed because we are increasing the frequencies, right? And we'll talk more on what is the frequency range and why it is getting tougher at higher frequencies. And yeah, so RF front ends, power amplifiers, filters, PLLs, at higher frequencies, we feel tough time in designing these stuff, right? So RF front end is a part of receivers, power amplifier is a part of transmitter, and without filters, we cannot even process stuff, right? We don't want, suppose we talking, right? We clearly, I think you're able to hear me. Whereas if you will tap into some other's call, if somebody else is there, why only you are able to hear me? Because of the filter. We are into some bandwidth, some desired bandwidth we are tuned into. So without filters, we cannot interact. We cannot get our channel. PL phase lock loops is a part of frequency synthesizer, which fixes the frequency. Precise frequencies is created by the PLLs, and a lot of innovations happens here. Recent years, phase lock loop got a lot of innovations here, so we can talk more on it, right? Even so, heterogeneous integration. Even Prince told about it. So I thought even without heterogeneous integration, I should also include it. So heterogeneous integration actually means usually what happens. Suppose we have a chip. Suppose we have a semiconductor chip, and then we have a package. So this is a semiconductor silicon, and this is the package. So usually a semiconductor pin goes into the pin. This is the pin part. So this is actually the 2D IC design. We actually, whatever we see in our phone or anywhere, the ICs what we see, it's a 2D ICs we see. And you see, this is the connection from the semiconductor to the outside world into the package, and this can be a gold connection. And you see there is a length, right? So obviously this becomes like an inductor actually. So this becomes an inductor, and high frequency, we still get lots of parasitics, and characterizing this becomes more and more difficult. So people went into some another solution. So what's the issue with this kind of chip? Since we are moving towards 5G, 6G, right, and beyond, we cannot stick ourselves to the 2D integration now. So that's why people went into some 3D, where you can see now we don't have this bond wire. Bond wire is not there. Now we are entering into directly, you call it a flip chip kind of configuration now we have. And why it is called 2.5D integration? Now the reason is now RF is designed by some other, let's say RF is designed in GaN, and MEMS is all the sensors, micro electrical mechanical systems. These are all our sensors like speakers, microphone, some of the transducers in camera. So that comes under MEMS. We have memory and a logic, means the microprocessor. So now inside, in place of having everything in one chip, we have designed different chips and integrated. So now that's why it is called 2.5D. So it's not going to exactly 3D. So but the future is like 3D. So what is happening if we have a 3D? We have now we can have a microprocessor here. We can have here memory. We can have here itself. We can have our RF, and here we can have our MEMS. All the sensors. So all the chips are stacked in the 3D now. Complete 3D happened here. And why it is important? We can clearly see that integration is happening more, and our connections are reducing, which is good because any connection results into extra parasitics, and we cannot go into higher frequencies. So, and another thing, what helps in 3D integration is, you can see the real thing. What helps in 3D integration is we can have different technologies like CMOS, GAN, and SiGe and FinFET, because not all the technologies have, like CMOS, which is one of the cheapest technology, right? So CMOS cannot provide everything good. CMOS have poor GM. We have poor GM in it. Transconductance, so electronic. We all are electronic guys, so we know what is a GM. So we have poor GM from it. Whereas if when you call BiCMOS or BG tree or heterogeneous devices, the GM is higher. So different technologies have different benefits. So in order to take all the benefits, the 3D stacking really helps. So this is what we are going towards, and I think I have seen still at 2D itself, lots of chip are still happening, but with time, because property of different technologies has to be utilized, we are moving towards 2.5D and a 3D, complete 3D. So that's what one heterogeneous integration benefit. And so AI is impacting semiconductor, right? So how AI is going to help us more? Uh, so any chip, as you saw in previous slide, that we have a lot of different components. Suppose you have a phase lock loop or a receiver or transceiver or any system, we have different chips. So we have different position. So what we have, we need to organize that in a floor plan. The layout has to be made. So, and what is very costly? The chip area is very costly. The cost all comes from the chip area. We all need to optimize our chip area without compromising the performance, without compromising the heat. Compromising the heat means we don't want heating issues. We don't want our clocks to get skewed up. So we need a floor plan such that we have optimized area, we have a very good clock distribution. There are a lot of things comes there. So what we do lots of iteration. It's a very laborious part of work. If anybody is there in the floor planning part, they know how tedious work it is. So now all the tedious work is taken up by the AI guy itself. AI itself can help us now. They will go through different areas and do some simulations to confirm that how much is the area occupied and how much is the latency and how much is the IR drop. All those things, what are the labor work we have in our chip floor planning part, can be taken up by the AIs. So that's a interesting part. And yeah, this also says that it also eats up some of the jobs, right? It eats up the job because he's doing lots of stuff. Optimization is done by them now. Floor planning, I was talking. So now second thing is a validation and verification. If you know this word, you clearly know that Indian job market is mainly based on verification and validation. And and it's very amazing that now AI can clearly do it. And since we are all here, lots of professors are there who did their PhDs. If they have done any design, they know that how much they need to go through tweaking. I mean, suppose they have designed something, and to get the performance, they tweak the circuit, and tweaking takes sometimes weeks, sometimes months. Tweaking means a random variation in the parameters so that we get good performance. And that randomness is a we all do tweaking, right? We all do tweaking because our technology doesn't exactly follow the mathematics. We don't have a square law model. We know that we have a square law model of the MOSFET, but square law model of the MOSFET doesn't work. So we do tweaking, and that tweaking is what we call it, trying to get the desired performance. And that is also tedious, right? So that labor work again, our AI can take clearly handle. So AI is going to help us in those areas where we need performance. So circuit optimization. So circuit optimization, again, this is a very this is not exactly happening till now, but in the near future, for sure, circuit optimize. Now we see analog designers says that AI cannot handle the analog because analog still have a lot of room, a lot of complications where AI cannot handle. So, but yeah, with time, I think even circuit optimization can also be handled by AI. And then what is the job left for us? Now, this is a very complicated question. Then what we will do if AI can handle the circuit optimization also? The point is we can do many things, right? We need to come up with something which we can improve, contribute more to the society, because labor work is done by AI now. So we should not think in that the job is taken up by AI, but yeah, we need to think something else where we can contribute to the society. So some work from AI I just introduced here, and this is some application from the future. So even neuromorphic stuff taken by Prince, he also pointed out this, where we don't have to go to lab for the lab test, right? We go to a lab test for our blood and sugar and urine test, right, to capture what what parasite we have in the body, which disease we have. So all those blood tests, even with time, with more complexity and more intelligence, I think people will develop a chip. They are developing. They are in the research part where lab on the chip itself going to get established. So which is a future application, and I think this is a part of where India is also moving towards. Even in my IIC, also some professors are working on these stuff. So these are in part of research. And RF and photonics for electronic warfare and communication. So this is all about um, very robust designs where lots of so military, we all know military means ruggedness. We need a reliability. We need, so if the extreme temperatures, we need our system to work. So yes, this thing has to be. This is what semiconductor is moving towards, and we are doing that. And so we need a more bandwidth, as we know 5G. So now we are moving in 5G, right? So 5G is still not completely deployed everywhere, but 5G is still in the progress. We are going towards 6G, and so then going to beyond. So what is meaning of 5G here means our all the circuits like receiver, what we have, the receiver has LNA, mixers, baseband amplifiers. So those has to operate at near 6 gigahertz and 28 gigahertz. That's the 5G. And anything at more than 10 to 12 gigahertz, designing becomes really, really complicated, because now what is happening is your signal wavelength and the dimension of your circuit now coming comparable, right? When it becomes comparable, transmission line effects starts. You need to take care of every length, right? Because at every 45 lambda by 4 length, the transmission characteristic changes. So that's a very complicated part. And if even if there is a small change in the length or parasitic, all the signals characteristic changes. So at higher frequency, the design becomes more and more challenging. So that's what 5G and 6G. When we talk about 6G, I think 6G is more and more beyond. It's going to go to 100 gigahertz, and I think even the 5G is in the research. 6G is also in the research. I have seen people working on LNAs and power amplifiers working at 100 gigahertz. People even claimed terahertz of signal. So where my strength is not there, uh, I'm working towards it, because even I want to understand what happens, what all the toughness happens in the high frequency range. I knew I designed few high frequency circuits, and I really faced a very tough time matching the spec. So yeah, so high frequency stuff is really a challenging stuff, and there are a lot of application going to come up. So from here, I think we can have some interactions, mainly for people who are into circuits and who knows what is a MOSFET, because I'm a circuit guy. And the main thing that I wanted to say here is, yeah, we have very tough time in innovating anything more in analog circuits. So analog circuit mainly has op amps, current mirrors, cascode, telescopic op amp, right? We have all those stuff. So innovations are happening very slowly happening in this area, because these are fundamental blocks of any system. They are fundamental blocks. So whereas really the innovation is going to happen in the application level. So application level, so we need to come, application level means we are actually solving a problem. So application level means that you are actually utilizing your analog devices and your basic system. I should call it subsystem. Let me call this a basic block. So these are basic blocks, and we have subsystems. Subsystems, so innovations, let's say innovation happening here as a one star, I should say. So very slowly, very hardly, I have seen innovations happening in the basic block. I have seen out of 5, I'm giving some stars. So I should say 3 stars, it means innovations are still happening in these areas, in the receiver, in the phase lock loop, active inductors, LDOs, and PLL. Innovations are happening here, but I should say, in the application level, this is 5 on 5. I should say 5 on 5 here. So a lot of innovations happening in the application level. Like I should just give a simple example. In our lab at IIC, I worked on FMCW radar. I think I'll go a little bit more on it if time permits. So here we are trying to solve a problem where we need to detect a heartbeat even through wall. So I'm not seeing the person, but signal is, the radar is inside a room, and a person is inside let's say he's in the washroom. So I cannot see him, but my radar should be able to capture the heartbeat of the person, so that uh, it has a great application, right? You know the person is healthy or not. And if somebody fallen, then you know that somebody is fallen and his heartbeat is going low. So this is the problem statements that I just told you. So this is what happening in my lab now. So application wise, we need to find a problem and do the solution, and that will become innovation. So innovation wise, a lot of innovation is still happening in the system, in the application level. Subsystem happening. So I have seen lots of IEEE transaction paper on phase lock loop recently. They have come up with different architectures. All digital PLL is also there, which get helps from shrinking technology, right? We are shrinking. Lots of technology devices are shrinking, so we can get help from the shrinking, because all digital phase lock loop is obtained. But yeah, all digital phase lock loop has some limitation. So yeah, we can talk on that. And I'll just focus a little bit more on why unlock cannot shrink. Because unlock cannot shrink because we all love so this is a gain of this simple op-amp. This is taken from the Razavi textbook. I just wanted to point it out why analog cannot shrink more. So this is a gain. So we love our GM, and GM is going to go down the moment we are going to shrink. So obviously GM is going to go down, and this is a R naught again, the output impedance. So output impedance is going to go low again. So effectively our gain is going to reduce. And if you know from our fundamentals, we really required our gain. So without gain, all the analog guys will become sad, because we without gain is everything to us, because we need to amplify the weak signal to the desired one. So that's the main thing. And another thing, let's say this is the noise expression. This is the noise, input referred noise of the circuit, we can see. So usually what is meaning of noise, I'll just point it out a little bit more. Let's say this is our noise level. I'll just say KTB. Let's say this is B bandwidth frequency, KTB. So this KTB is a noise. And let's say I'll just take some numbers also. It will make more sense. Let's take it minus 90 dBm. So 90 dBm is a noise level. And clearly, to have a 10 dB of SNR, we want our signal of desired signal to be 10 dB higher, right? That's a 10 dB SNR for us. So point here is, if the GM itself is shrinking, so clearly we can see our noise is going to increase. So obviously our noise level will go up and our SNR is going to go down. So this is what the trouble with the analog guy. One of the trouble with the analog people that they are going to face, because as technology shrink, we suffer from high noise and a low gain, right? So just to elaborate more, where is analog, where is RF, and so this is one of the simple block of transceiver, right? I should just divide them. So here we have a transmitter portion, and this red block is a receiver portion. So now this is your digital signal processing portion, and this has all the communication people. They all know about. We have QPSK here. Any kind of data, if you send, we send through QPSK or any modulation scheme, OFDM, so etc. There are lots of stuff here. So different modulation schemes are there. We put them. That's a part of digital signal processing itself. We need DAC. This we call it mixed signal. All the mixed signal guy works here, making a good ADCs and DAC. And here it's a filter portion. where we can also call GMC filters. GMC filters made up of active elements, GMC filters, and now it's a mixing high frequency mixers, and this is a high frequency adder. It's a high frequency analog adder. It's not a digital adder, it's analog adder. And now it's a high power, high frequency power amplifiers. And there is a one guy which we call LO, is actually what the frequency generator is. So my research actually focused mainly on frequency generator and the receiver portion. So LO is usually done by the PLLs. PLL generate the frequencies for us, and usually the core thing is the VCO, right? So VCO is a voltage control oscillator whose phase noise is usually very high. The VCO phase noise is high, and PLL is helped to reduce the phase noise. So that's what happens. PLL helps to lock to one frequency and reduce the noise of the VCO so that we can use the desired frequency to up convert or down convert. So here in the transmitted portion, actually up conversion happens, right? The up conversion happen in the transmitter. So here we have so all the low frequency data. Till here we have low frequency data. We can call it like less than 1 megahertz signal will be there, and LO will be whatever technology we are in. Let's call it 2 gigahertz. So LO is at 2 gigahertz, and this will get transmitted. So when mixing happens, let me just even say, I think these things are known to have. I'll just point. If the mixing happens, it does something like this. The mixer just creates a output which is a sum of the frequencies and subtracted from the frequencies, right? So this is what we'll get. And power amplifier. So later stage, I think we're going to have some filtration. Some filtration will happen. We'll either take, since it's up conversion, we'll surely take F1 plus F2, and it is transmitted through a power amplifier. So that's the transmitted part. And so antenna, so we have antenna, which is, I think it's a duplexer. So with the use of switch, simultaneously we can switch to even LNA. So now the signal will come to the LNA, right? LNA obviously receives a very low signal. I'll just point it out again here. So the LNA, if it is a GSM, it also receives like minus 100. Let me first say that what is the minimum signal strength required for our GSM. So I'll just say minus 110 dBm. Now you see the minimum signal that is required by our LNA itself is minus 110. It means the noise, to have a 10 dB of noise figure, so a 10 dB of SNR, this should be at minus 120. Now you can see minus 120 dBm is a very, very low noise. So clearly we required a system from here to here which generates very, very low noise, right? So it's very tough to design very low noise system, and we cannot rely on shrinking technology. We need to go beyond shrinking technology. That's what more than more means. We need to use some good technology like SIGI or GAN so that we can reduce the noise and increase the performance. So here main part was I thought of showing you what is called analog and mixed signal. This is analog and mixed signal. We have RF and LNA. So that's what it is. So there is one interesting stuff that I thought of asking, if it is not asking, I'll just speak on. So let's take the LNA first here. So what LNA really does is we have an antenna here, and then we have an LNA. Usually, let's say it is working at 2 gigahertz. So antenna is usually designed to be at 50 ohms. So this ohm is not a physical. This is actually something I'll just roughly just give a name, L by C, inductors and capacitance. Inductors and capacitance. So from where the noise is coming, I just told, right, the noise has to be low. Whereas noise is a part of all noise is always generated by a lossy element. Whereas our antenna is not at all a noisy element. It's only made up of flat. There is no physical resistor. It's just at our desired frequency of operation, we get 50 ohm. And so the point here is if this is not actually a resistance. This is actually impedance which is at our desired frequency, and it's a characteristic impedance. There is no physical resistor. It's just LNC. So because of that, we should not see noise coming into the play. You see, 4kTr is a noise which is also entering into the LNA. We used to say that 4kTr is a noise which should enter into our LNA, but the question is there is no physical resistor, right? So this is one of the interesting thing that I discovered, and I thought of even showing you that, yeah, there is no physical resistor, but still we say 4kTr is our noise. So I think only antenna people know that actually this antenna people may say only antenna guys know that this 4kTr is not coming from the resistor because there is no physical resistor in the antenna. It's actually coming from the outside, which is equivalent to 4kTr. So I don't have more on it. I just want to point it out that really a noise source has to come. Any noise source should be a lossy element, but antenna is very less noisy. So if I'll say resistance of antenna, even if I want to calculate physically, it will be just 1 ohm, right? Antenna cannot be lossy more than 1 ohm, but our noise always says 4kTr and R is 50 ohm. We are stick ourselves to 50 ohm, right? Input and output impedance has to match that 50 ohm. That's what we all say. So this is what one thing that noise is equivalent noise comes from the environment, and that it's not from the antenna. So that small thing I wanted to show. And here some phase noise stuff. Just to point out what is a phase noise and how it impacts digital and analog circuit. So mainly phase noise. So okay, I'll just take very fundamental stuff. Phase noise means what, and jitter means what. So phase noise means ideally our signal is, if I want to generate a signal, ideally our signal is sine omega naught t. So omega naught is a pure frequency, and in the frequency domain it will just visible to be a clear tone. But in reality our signals are we have some variation in the phases. Because of that, we will never see a clean tone. We will always see some noise. So this portion where we are expected to have one tone, but we have some noise frequency component even at higher than desired frequency. And this is what we call the phase noise. So in time domain sense, if you want to point it out what is a noise means. So in time domain aspect, I'll show in with respect to our clock itself. So usually we talk T is a time period of the clock, but because our time, the frequency itself is what? 1 upon f, right? The frequency itself is not a constant element. We see the frequency has some variation. So obviously that means what? We have some variation in the rising edge and the falling edge. So obviously now we are restricted to T minus some Tj, jitter. So jitter is a time domain concept where so this is so actual time period is T minus T jitter, and we expect that our data, so this is the clock with jitter, and if I want to send a data, let's call it theta, my now theta has a no choice saying that it has to reach the other input by T minus T jitter. So the distal people totally focuses on jitter, that how much low the jitter can go. And recently what I have seen is people also went to 100 femtoseconds. 100 femtoseconds, sub femtoseconds of jitter they are able to achieve. And yeah, there's very challenging part to get to these numbers. 100 femtosecond is not an easy thing to reach. And in my lab that I have done, I was just able to reach just 900 femtoseconds, which is very tough to reach this number. And I was not impressed by my own numbers when I saw how people have went through lots of different techniques to reach these numbers. So in distal domain, we call it jitter, any noise in the clock. And these are actually generated by the circuits itself, device itself. So I'll just rub this just to say it. And
Sumit, we have four more minutes, so probably
Right.
can wind up and then move to Krishna.
Right, yeah, sure. So in analog, this is a RF block where you can see our desired frequency is not exactly at one tone. Now it is had spread, right? You can see it has spread. This is the yellow portion of the circuit. So this is the yellow portion. And when we did mixing, we reached. So when we did mixing, what happened? Our desired frequency reached to the beat frequency. It reached to the beat frequency. But the blocker is any signal which is near to our channel, which has a higher strength. What will happen now? This also LO will also mix to this because we cannot avoid it because the signal is all coming. So the moment it mixes, we can clearly see the noise also enters into our desired signal. So clearly the our SNR of the desired signal again get reduced. So we need to design stuff which will again reduce the noise, right? So this is all what phase noise really means and how it impacts the receiver performance, because here you can clearly see there is a degradation, and phase noise also impacts our digital domain, and circuit techniques are uh, keep on innovation is happening to improve the SNR in the analog domain and jitter in the digital domain. So conclusion here is I want to conclude now. Conclusion here is application level circuits are still evolving, and at higher frequencies circuits are still evolving. So so we still have room to learn and improve more. So I think I should conclude here. I think this is the end.
Yeah, thank you,
Yeah.
Sumit. We'll have questions from the participants. There is one from Mr. Vishwajit in the chat box. I'll read it over. Is it correct to say that more innovations or topics of research are available in SOCs and digital domain than analog and RF?
I should not say this. It's not like that actually. A digital domain, you can see a lot of things are happening in analog digital domain also. It's not like analog is analog. See, we usually when I was in the initial PhD guy, I used to think everything is getting saturated. Lots of innovations already happened. So the point here I wanted to say here is think about in place in terms of application. When we talk about application, now I'm not saying the analog or a digital. So take a problem. I think if the solution exists in the digital, it means innovation still exists in the digital. If the problem solves in the analog domain, I think then innovation exists in the analog. So I cannot comment like that. I should say which problem you have and which domain it's going to solve. So the solution is innovative, and either it is digital or analog. I don't think that is any comparison like this.
Yeah,
Hope this okay.
yeah, Mr. Vishwajit, hope you're right. Okay. Okay. Any more questions? Okay. I think there's no more questions. We'll wind up the session.
Right.
So I would like to thank Dr. Philip, Prince, and Mr. Sumit for delivering this first session, which introduces the topics of the innovations happening in the semiconductor domain. We were fortunate to have two people, one focusing on the digital domain, and Sumit focusing on the RF domain. So we will have later sessions on both these areas. So hope the participants can connect to what has been taken here and with whatever is going to be addressed in the later sessions. I'll take this occasion to thank once again Dr. Philip and Mr. Sumit for agreeing to be part of this FTP and share their knowledge with the participants. Thank you.
Yeah,
Thank you, sir. Thank you for inviting us to deliver talk here in this platform.
Okay.
Yeah.
Yeah. So we will wind up this session. We'll start the next session. We'll take a short break and start the next session probably at 8:05.
Good evening, all. Hope I am audible. Okay, welcome to the second session of the day one of the FDP titled Secure and Intelligent Systems on Chips. The second session is on the topic hardware for artificial intelligence, and